Welcome to the Explainer. If you are currently navigating these somewhat treacherous waters of calculus, you know that power series can feel like a massive hurdle. Well, we're going to tackle this together. We are diving deep into the Student Guide to Series today, and we'll be unpacking one specific, surprisingly tricky mathematical example step by step. We really want to see how the mechanics under the hood actually work. So right off the bat, here is the core mystery we are going to crack today. How is it possible that one single, simple function can behave completely differently just depending on how we set up the math? You'd think a function is just a function, right? But as you'll see, the second you translate a function into a power series, the perspective you choose changes absolutely everything about how that series behaves. Here's our quick roadmap for this explainer. We'll start with the geometric series trick, then look at case 1, centered at 0, followed by case 2 with a shifted center, uncover the breakthrough singularity rule, and finally avoid the endpoint trap. All right, section 1, the geometric series trick, forcing the function into form. This trick is really all about taking a function and just forcing it into a shape we already know how to work with. It's a classic algebraic manipulation, and it basically sets the foundation for the whole shebang. We start with our function, f of x equals 1 over x plus 2, and carefully twist it. We want it to look exactly like the classic geometric series formula, which is 1 over 1 minus r. To pull that off, we factor out a 1/2. That leaves us with 1/2 times 1 over 1 plus x over 2. Then we literally just tweak that plus sign into a double negative. Boom! It matches our template perfectly, where our r, our common ratio, is equal to negative x over 2. Moving right along to section 2. Case 1. Center at 0, expanding around the origin. Let's see what happens when we actually build our newly formatted series right here at the origin. Since our powers are just in terms of x, which, is basically just x minus 0, our center C is exactly 0. Our common ratio, r, is negative x over 2. And because of that, we can write out the full geometric sum. Just like that, we have successfully translated our function into a power series centered right at 0. Now, this brings us to a really key boundary, the number 2. Why exactly 2? Well, for any geometric series to actually converge, to, settle down on a real usable value, the absolute value of our common ratio, r, absolutely must be strictly less than 1. So if the absolute value of negative x over 2 has to be less than 1, we just multiply both sides by 2. That tells us the absolute value of x must be less than 2. Our little mathematical manipulation just literally handed us a radius of convergence of exactly 2. All right, section 3, case 2, the shifted center, expanding around x equals negative 1. So what happens to our function if we shift that perspective? We actually have to go back to the original function and do a completely different algebraic trick to expand it around x equals negative 1. We rewrite 1 over x plus 2 as 1 over 1 minus negative x minus 1. It's a pretty clever little trick. Now our common ratio, r, becomes negative x minus 1, which we can also just write as negative parentheses x plus 1. Because the terms are grouped as x plus 1, which is really just x minus negative 1, our center is mathematically shifted to negative 1. The series looks totally different now, but it still represents the exact same original function. But wait, check this out. Our radius is now 1. If we take our new common ratio and set its absolute value to be strictly less than 1, we get the absolute value of x plus 1 is less than 1. That means x has to be between negative 2 and 0. The radius of convergence we just found is exactly 1. Which leads us to a really crucial question. Why did the radius shrink from 2 down to 1? We are looking at the exact same original function. Literally all we did was change the center we were expanding around. Why in the world would merely shifting our mathematical center physically change the size of the radius? That brings us to section 4, the singularity rule, the physical barrier of power series. This rule right here is an absolute unbreakable law of calculus, and it dictates exactly how far a series can stretch. A singularity is simply the point where a function is mathematically undefined. So if you look at our original function, f of x equals 1 over x plus 2, what happens if you try to plug in a negative 2? The denominator becomes 0. The function completely blows up. It is mathematically undefined. I want you to picture this singularity as a massive, solid brick wall at x equals negative 2. The function simply cannot exist there. No way around it. And here is the universal truth that completely solves our mystery. The radius of convergence is always exactly the physical distance from your chosen center to that nearest singularity wall. Let's look at the math for a second. In case 1, our center was 0. The wall is at negative 2, The distance between 0 and -2 is exactly 2. In case 2, we shifted our center to -1. The wall is still sitting right there at -2. The distance between -1 and -2 is only 1. The radius shrank simply because our new center was physically closer to the singularity wall. Comparing the two cases side by side, like this, really makes the whole picture click. As the center shifts from 0 to -1, the radius shrinks from 2 to 1. But look at the intervals of convergence on the right side there. Both intervals hit their lower boundary at exactly -2. Neither series can ever stretch past that singularity wall. This is a massive aha moment when you're trying to understand power series. Finally, Section 5, the endpoint trap. Why perfectly good numbers fail. Now, this is the #1 trap students fall into on exams, for sure. We know our series works perfectly inside the radius, but what happens exactly on those boundary lines? Look at the right side boundary of case 1, which is x equals 2. If you plug 2 into the original function, 1 over 2 plus 2, you get 1/4, which is a perfectly valid, well-defined number. But if you plug 2 into the power series, it completely diverges. How is it that the original function works perfectly fine, but the series representing it just completely fails? Well, this happens because of the absolute strictest rule of geometric series. They only converge when the absolute value of the common ratio, r, is strictly less than 1. At the left endpoint, x equals -2, our ratio r becomes exactly 1. That creates a series of 1/2 plus 1/2 plus 1/2 going on forever. Obviously, it diverges. At the right endpoint, x equals 2, our ratio r becomes exactly -1. That creates an alternating series, 1/2 minus 1/2 plus 1/2. You get the idea. It never actually settles on a value, so it also diverges. Because the absolute value is exactly 1 in both cases, it steps outside that strict geometric condition, even if the original function is perfectly happy at x equals 2. So this brings us to the ultimate golden rule. If you remember one thing, make it this. The singularity determines the radius, but the geometric series condition determines what happens at the endpoints. The brick wall tells you how wide your interval is going to be, but to know whether those specific boundary endpoints are actually included in your interval, you always have to check them individually against the rules of the series itself. So I'm going to leave you with this final thought to chew on as we wrap up. Where's the nearest singularity in the very next function you'll face? The next time you sit down to tackle a power series problem, try not to just blindly crunch the algebra right out of the gate. Find the center, look for that brick wall. Once you know exactly where the singularity is, the rest of the puzzle pieces start falling right into place. Thanks for joining me as we worked through the Student Guide to Series. Taking this framework and just looking for that singularity first, it completely changes how you approach these problems. See you next time.